Hello, welcome back to the second week workshop of McMedHacks 2023. We're actually going to just start immediately. I'll do my usual housekeeping at the very beginning. Ooh, hello from Bangladesh. Nice to meet you. We have our one of our postdocs from the Enger Lab at McGill Medical Physics, Dr. Parsa Bagherzadeh, to have instruct our workshop today. I'll just do a quick introduction and a housekeeping. Whoops, not trying to show you my code here. Let's this. Okay, so I will start the presentation. Today is June 18th. This is the first deep learning fundamental workshops that we're going through. Again, if you have questions, please feel free to email us. And I hope you at this point have some familiarity with classical machine learning, as well as the basics of image pre-processing from what we have provided on the Gumroad platform. So today is the first official workshop that you'll have experience with PyTorch, as well as some of the theory behind it. So just to let you know, we're in phase 1 of the summer school, week 2, and right now introducing the deep learning framework, PyTorch, more specifically on the building of neural networks and the fundamentals of all that, training, evaluation, just the workflow in PyTorch today. So this is where we're at in terms of the entire workshop. And just to remind you, we have 2 mentors this week, Ni and Sami. And if you have received the Eventbrite emails from yesterday, you'll also see the link for the tutorial for this coming week. They will give you help on Thursday at 1:30 p.m. Eastern Daylight Time. So please adjust it to your own time zone if you have any questions to ask them. So just let me introduce our instructor today, Dr. Parsa Bagherzadeh, who is a full postdoctoral fellow at McGill University at the Medical Physics Unit in our lab. He is, as I said, a postdoc in our lab, and he focuses on natural language processing techniques to leverage clinical text reports for cancer treatment outcome prediction. He obtained his PhD in computer science from Concordia University under the supervision of Professor Sabine Bergler, and also a proud member of the CLAC, Computational Linguistics at Concordia Lab. During his PhD, he focused on the integration of external knowledge sources for language processing, specifically biomedical text processing. And he also has a master's in artificial intelligence in Firdausi University of Mashhad in Iran, and a computer science degree and computer science bachelor's degree as well. So you'll see him two more times for the 2 workshops in the second phase as well. So this is the first one that he's giving. And thank you so much, Parsa, for your time and dedication for this workshop today. I'll just start sharing you can start sharing your screen now. And just for our participants, I've received a few requests to record a meeting. I just want to let you know that these meetings are all recorded, and we'll post them on our YouTube channel, so you don't have to keep requesting it. So thanks. All right, please go ahead.
Thank you, Eugene, for the introduction. So can you hear me?
Yeah, I can hear you pretty well. Okay. Yes, there'll be quizzes for attendees who miss live sessions. We will update you all on that.
Okay, so hello, everyone. I hope you had a great weekend so far. So let's jump into our tutorial. So welcome to McMedHacks. Today we are going to talk about deep learning fundamentals. I'm Parsa. I'm a postdoc at McGill University, as Eugene introduced. So I guess this slide is a little bit useless, but thank you, Eugene, for the introduction. I'm focusing on medical informatics, natural language processing, and deep learning applied to precision oncology. So let's talk about briefly about the history of ANNs, or artificial neural networks. ANN they are in contrast to NNNs, natural neural networks. So these natural neural networks are basically those biological neural networks that we have in our body. And these ANNs are inspired by such organisms in our body. The first attempt for modeling how neurons in our body and in our brain might function and might work was in 1943 by McLaughlin and Pitts. They can be considered the fathers of ANNs. And then we had in 58 Rosenblatt proposed perceptron, which was a huge step at that time for the ANN community. Later, until 80s, maybe the learning of ANN, it was limited to single layer networks mostly. However, introduction of backpropagation algorithm allowed to train multi-layer nets. However, because of the difficulties of backpropagation and training of multi-layer nets, ANNs fell out of favor in 1990s, as we refer to it as Winter AI. AI Winter. And then there was a renewed interest in the 2000s in deep models because at that time the hardware and the availability of data and also the introduction of new techniques for training of neural nets allowed to train these models. And after 2010, we had a booming of these models, and models such as GANs, autoencoders, and transformers revolutionized AI. And you can see the products of transformers today, as one of them as ChatGPT. So first, let's talk about the simplest neural net, single layer feed-forward network. So a single layer feed-forward network is basically a simple multiplication. So we have a matrix W. This matrix W has this shape D of in times D of out. It means it has D rows and D of in rows and D of out columns. This projects its input to an output. So just like a simple function, just like all functions, a single layer net basically has an input and has an output. It has a projection that projects the input to an output. Formally, we write down this operation like this. We have an output Y. We are multiplying X by W. So this W, we call it a weight matrix. This is learned during the training process, and this is learned such that we can approximate certain functions. So we are multiplying X by W. All of these multiplications are in vector space and in matrices, in matrix spaces. So all of the rules that we have for matrix multiplication, they hold here. Rules such as compatibility of the product, and so on and so forth. So here we have a function. For now, let's assume that this function is an identity function. What do I mean by identity function? It means that it doesn't change the result of this product. Whatever I have as a result of this product here, X times W, it doesn't alter the result of that product. So a question here is, why we are calling these, if it's a simple matrix multiplication, it's why we are calling it a network, and why we are calling it a fancy name. So let's see what's happening actually when we are multiplying a vector by a weight matrix like this. So when we are multiplying an X by this matrix W, we are multiplying this row by this column, right? So when you are doing this, we are actually doing the dot product of this row and this column. So if you pay attention here, this element here is multiplied by the first element, okay? And the second element is multiplied by the second element, and so on and so forth. And the results are aggregated here. The results is aggregated here, and we have we are adding up all of these multiplications. So if you follow this path, we have a net-like connection, net-like connections here between these the input and the output, connected by a by a weight here, which is these values are basically trained. So we further abstract this concept into a net-like illustration. But overall, a neural network is nothing more than matrix multiplications, or a set of matrix multiplication. Our input is multiplied by a weight matrix and is mapped to an output. Okay. So at this point, let me introduce the TensorFlow playground. Let me briefly talk about what is TensorFlow playground and look at the simple neural network. Okay. So TensorFlow playground is a platform here, is a visualization tool that allows you to configure certain simple neural networks and look at different architectures here. So here I have a simple neural net. It has 2 input and it has 1 output. I would talk about how to determine the number of inputs and outputs and the number that you have in between. But for now, consider this setting. So the problem that we are interested in and our objective is to find a separator, find a line or a hyperplane, because when we are talking about in 2 dimensions, we are talking about lines. A line can separate these two set of samples. But when we are going further in higher dimensions, we need to talk about hyperplanes. So the objective is to find a separator line or a separator hyperplane. Okay. So here, if we start a training process, you can see it can easily, a very simple neural net can easily find a separator between the 2 classes. Okay. But however, this is a very simple distribution. These two classes, these 2 set of samples are linearly separable. This is the term that they can be separated by a line. However, how about this? Are these 2 set of samples? Can they be separated by a line? No, they never. They won't be separated by a line. So what is the solution here? The solution, let me share my whole screen and then I can avoid this jumping back and forth. Okay. So what is the solution? The solution can be found in changing the structure of a neural net. Instead of having one projection and a single layer network, we can increase the number of layers and have a multi-layer feed-forward network. When we are talking about this multi-layer feed-forward net, it means that we have, instead of one projection, instead of one mapping, we have several mapping. Before we had an input layer and output layer. Now we have an input layer, two hidden layers here, for instance, for this network, and an output layer. Each layer here can be characterized and defined by a projection. So here I have my first mapping, my first projection. X is mapped to H1. Here depicted like this. X is mapped by H1 by W1. These set of weights that I have here. Then H1 is mapped to H2 by W2, and H2 is mapped to Y by W3. Okay, so we have now we have consecutive projections, and we have, as they call it, made the network deeper, and we have increased the number of parameters, hoping that we have given the network more discriminative power. Okay, so if you have heard about deep learning is supposed to find ideas, find concepts and features, and basically separate very complicated distributions, and define basically very complicated distributions. So let's see whether if we increase the number of hidden layers, if we increase the number of parameters that I had in my network, can I increase the learning capacity of this network? Can this network, now that is more complicated, it is more deeper, can it separate the two classes, the two distributions here? Let's see. It doesn't seem that it can do it. Even though I have increased my number of the number of layers, even though I have increased the number of parameters, learning parameters, even I made my network more complex, or I thought I made my network more complex. The question is, did we actually increase the learning capacity? No. Why? Because if we look at the set of projections that we had before, first starting by this projection, we can rewrite Y as this, right? So H2 was multiplied by W3, so H1 was multiplied by W2, and X was multiplied by W1, right? So I have X, W1, W2, W3, the consecutive projections that I had. So, and we can substitute this W1, W2, W3 with a W tiled. And we have this form. We have Y equals to X W tiled, which is actually the form of a single layer net, right? Before it was the form of a single layer net, right? And this multi-layer network is reduced to a single layer network. And this shows that deepening of a network does not necessarily lead to more learning capacity. As I illustrated on the TensorFlow playground, I increased the number of layers, but no success was achieved. So you remember that I had an assumption at the beginning that assumed that f is the identity function. So when we are assuming that our function to be an identity function, actually our network would always be a linear network, would always approximate linear functions. But there are some certain cases that the function and the distribution is not linearly separable. So to remedy that, we use activation functions. Activation functions are often used to add nonlinearity to a network. So instead of assuming our function is an identity function, we can that it is one of these non-linear functions. Okay, so this is not the set of all activation functions that exist out there, but these three activation functions that are the most common and the most widely used activations out there. So we have hyperbolic tangent. Hyperbolic tangent squashes or maps its input. Any value that you give to this function, it squashes the input into the -1 and 1 interval. It doesn't matter if you give minus 1000 or plus 50, it always would be in this interval. Then we have sigmoid. It maps the values between 0 and 1, this interval. And we have ReLU activation function. So ReLU activation function is overall, it's a non-linear function. However, it is a piecewise linear function. So from minus infinity to 0, it is 0. And from yeah, please mute yourself. So from minus infinity to 0, it is 0, and from 0 to plus infinity, it is a linear function, and it's equal, and the function expresses y equals to x. But overall, it's a non-linear function. So the use of such activation functions and non-linear functions gives the network the ability to approximate more sophisticated functions. So the functions that are potentially are non-linear separable. So how we are using these activation functions? These activation functions are applied to output of each layer in an element-wise fashion. So suppose the output of an arbitrary layer is this. So the outputs that we have here. Because the output of the first layer is H1. H1 is here is a vector, right? So suppose we have a three-dimensional vector like this. This is an arbitrary, the set of arbitrary numbers. If we apply the sigmoid function, as I mentioned, it maps all of the values between 0 and 1. So -1 here, something is -1 is 0.0044. It is almost here. It is mapped to 0.2, right? So 0.88 is here. It is mapped to 0.70, and 1 is a little bit farther, and it is mapped to 73. So activation functions, after you produced, after you did your multiplication here, you apply the activation function to the output. Here, this assumption that I had before, after you are doing your multiplication, you are doing your projection, then you are applying that activation function of your choice to the elements in the vector. Okay. So, but and a very important question. I told you that don't worry about the shape of the output and the number of outputs, but for a classification problem at least, we can later talk about regression problems as well. I know that Dr. Azizi, in the previous session, she talked about a classification problem and the regression problems, and what is the difference between the two settings. But for now, we are turning our attention to a classification problem. So in a classification problem, what defines the shape of the output, or what defines the number of outputs? Actually, the number of classes that you are interested in defines the shape of the output. So your samples are annotated and labeled by the experts into how many classes. Do you want to separate between how many different phenomena or objects? For instance, if you want to distinguish between bananas and oranges, so you have two classes. If you want to add another class like apple, you have three classes. Then you can add all of the fruits that are out there, and you have more than many more classes. So traditionally, if we have only two classes, If you have two classes, we can use a single output with sigmoid activation at the end. So there's you're giving your input, then you are doing some projection. Here I have one hidden layer, and then this hidden layer, the output of this hidden layer is mapped to the final output of our network. Okay. And then this, whatever you have as an output, you are passing it through a sigmoid activation. When you are passing something in through the sigmoid activation, as I mentioned, it is being mapped between 0 and 1, right? So how we can decide which class corresponds to this sample? We can put a threshold at 0.5. We can say if it is greater or equal than 0.5, it is class 1. If it is below this value, it is class 0. So using only a single output, we can do binary classification. However, if we have more than two classes, and in fact, if we have C classes, we can have C outputs with a softmax activation at the end. So each of these outputs, they represent some sort of a score for the corresponding class. We can have a correspondence between a neuron here, an output here, and a class. We can assign this neuron to be class to correspond to class 0, for instance, or class 1, this to class 2, and this to class 3. So the output here, before applying softmax activation, I will talk about what is softmax in a minute, but the output before, the raw outputs are often called logics in a network, okay? So those are raw outputs that can have any values. So then we apply to this output, which is a vector like this. It can be in D dimensions, or in our case C dimensions, okay? H1, H2, and to HD. We can apply softmax activation. The softmax activation, the purpose is to map all of these values, these output values, to 0 and 1 interval, such that the summation of these new values are summed up to 1, which reminds us of probability, right? The summation of different, the summation of the probability of different events. In our case, the event is being the member of that class, should sum up to 1, and it shouldn't be greater than 1, because the addition, the summation of all possible events shouldn't go up greater than 1. Okay. So how we do it? We take the exponent of each of these elements, exponent of H1, H2 till HD, and we divide it by a normalization factor, and we normalize it by this factor, which is a summation of all of these values, right? So overall, each of these would be lower than 1, and the summation of all of these values would be 1. And we would choose the output that has the highest probability as the winning class. So now we know how to do prediction for a network. We pass the input through that consecutive set of projections. If there are any activation functions, we apply those activation functions, and then we take the output and whether it's a binary classification or a multi-class classification, we can decide which class to assign to this sample. However, well, how we actually do the training, because so far my assumption was that all of these projections, they have been learned, they have been trained, okay? These W1, W2, W3, these all of these projections, all of these weights that connects the input one layer to another layer, they should be trained. But how we should train? So we need to adjust. We need to adjust these weights. But how? So we need to use loss functions. So what is a loss function? Loss function basically measures the closeness of the predictions that we had and the target that we want. Okay, because you might give an image of a brain scan to your model, and the model might assign no tumor found and predict no tumor. But the point is that there is a tumor inside this image. There exists a tumor. So we need to adjust the weights and the parameters of the network such that the network actually predicts the tumor. Because we want to later deploy this model in a clinical settings, right? So we use this loss function to actually measure this prediction and what we desire. Our desired target. So some of the loss functions that are very common are MSE, mean square error, cross entropy, hinge, and hover, depending on what is your problem, what is the problem at hand, classification or regression. We would have different choices. For instance, for regression problem, there is one common loss function is MSE. For classification, for instance, is cross entropy or hinge, and so on and so forth. But in our tutorial, we would use cross entropy loss. So cross entropy, again, it measures the closeness of the prediction and the targets. Suppose so we are denoting a loss, the value for loss using this L, which measures the closeness of the target Y and the prediction Y hat. I'm showing my prediction by Y hat. So and basically is defined by this formula. So it is a summation on the predicted value for different classes. So suppose you have a 4-class classification problem, and the annotator and the expert has labeled your sample as class 1, right? As class 1, because the other classes are indicated by 0. This is a one hot representation that the entry that has non-zero value, it corresponds to the corresponding class. But this is the output of my network. Okay, it's and if you can see, if you sum these values, these are summed up to 1. So our model is 30% sure that it's class 1, 40% sure that class 2, 10% class 3, and 20% remaining as class 4. So in fact, our model is a little bit wrong. The model is not very wrong because it is almost sure that it is class 1, but it fails to make the correct prediction. So we need to measure how much the model is making a mistake. So the corresponding values here, the corresponding value YC, the first element here, is multiplied by the log of the first element here. Okay, 1 times the log of 0.3, 0 times the log of 0.4, 0 times, and so on, so far and so forth. So the summation of this, the summation of all of this is minus 1.73. And since it makes sense that our loss and error would be positive, we are multiplying this by a -1, such that we have a positive number. So this loss, we calculated the loss. We have 1.73 loss. The value of loss is 1.73. Then we need to minimize this loss because we don't want to have any loss. Okay, we want to have the prediction of we want to have a perfect prediction for our model. Okay, and in fact, we want to have the same prediction that prediction as the target. We want to be absolutely sure for the class 1 and 0% sure for the rest. Okay, so if we assume that we are absolutely sure and the prediction of the model is 1 here and 0 here, actually the value of the loss would be 0. So in the ideal case, the value of the loss should be 0, and we need to minimize the loss. But how to minimize the loss and how to optimize our network? So remember when we are interested in minimizing something and minimizing a function, we need to see this function is expressed by what? What are the parameters of the function? What are the variables of the function, right? If we change the variables of the function, if we are interested to see which values are minimizing a function, we need to take the derivative of that function. And we need to take the derivative of the loss. Why? Because the loss is basically here is a function of what? A function of our target and a function of our prediction. So if we assume that the target is always the same during our learning process. So this is a constant. Y is a constant. So actually the loss function is a function of the prediction, and the prediction itself is a function of all of the learning parameters that I had in the network. So I need to, if I want to minimize this loss, I need to adjust the parameters of the network. How? By taking the derivative. If we remember from the first calculus course that we had, Calculus 101, if we want to find the minimum of the function, we only need to set the derivative of that function to 0 and find where that function for which values that function the derivative is 0, and then at that point we can say, okay, this is a minimum. This point is yields the minimum for this function. However, this is too good to be true, because ANNs often describe non-convex function. So this is the difference between a convex function and non-convex function. This is a quadratic function, which is also a convex function. A convex function has only one minimum. However, non-convex functions that are more sophisticated functions, they have several local minima. So we cannot just take the derivative like we used to do and get the minimum, right? So a solution to this is to instead use an iterative process called gradient descent. So gradient descent tries to iteratively update the parameters such that our error would be minimum. So remember, we want to minimize the loss. Here I'm depicting and I'm illustrating a surface for my error and my loss function. And here you can see that the loss is represented by the network, by the learning parameters of my network, which I refer to here as theta or W or any other learning parameters that you have in your network. And initially, when we are starting the training process, our loss is somewhere here, depending on what is the value for the learning parameters. So, but we need to find another value for the parameters such that our loss would be reduced. So, to do this, we use the gradient. We use the gradient of the error or the loss function for the set of current parameters that we have at the moment. Okay, so the gradient is actually shows the slope of a function. It shows where we need to head to get a smaller value for our function, and what is the direction of the reduction in our function. So for the current parameters, for the current error, we can take the derivative of we can take the gradient of the error based on the current sample, and then use that derivative to update the parameters of our network. So suppose that the old set of parameters that I had, I'm denoting it with theta old. Then the value, this is the value of the gradient. The value of the gradient actually shows, again, the slope of the function where the function is declining. Okay. And then with the step size, or what I call learning rate, depending on how much we want to change and with what magnitude I want to change the current value, I can move on this surface. So here I can go down with a greater magnitude if I choose a greater value for this eta, which is, I'm calling it learning rate and is referred to as learning rate. Or if I choose a smaller value, I would go with the slower steps, with a slower pace. So we would have an iterative process. We would start from somewhere, then we are passing all of the values, all of the samples that I have and we have in the training set, and then we gradually get a better estimate for our parameters. So, and note that if you have started from here, we would end up probably here, right? If we start from this side, we would end up probably here. That's why we cannot basically take the derivative, because the ordinary derivative and the classical approaches for finding the minimum, because we have multiple or several local minima. Okay. So then now we know that how to update what is the gradient descent and how it is used to update the parameters. Note that the gradient descent can also be used and applied to convex functions. Why? Because we can. It's a more general framework. It can start from here and then it would end up at this minimum. So this gradient, we are not very worried about calculating this gradient, because most modern deep learning libraries automatically calculate the gradient for us, and we don't need to do it manually. So what is the next step? The next step is to actually apply this. So before here, we calculated this gradient, but the applications and applying this gradient and getting the new values for our model is basically commonly done by optimizers that most deep learning libraries provide. So these optimizers, we provide the gradient of the loss to these optimizers, and these optimizers are responsible for the update of these values. And different optimizers, we have different optimizers like stochastic gradient descent, RMS prop, adaptive momentum, so on and so forth. So each of these optimizers, they have a different scheme for the update of the parameters. But however, most of these optimizers, or all of these optimizers, are based on gradient descent. So when I'm talking about different scheme for the update of these parameters, it means that some of these optimizers, they converge faster and they find the minimum faster, and some of these optimizers, they fail to converge toward a minimum. Some of these optimizers are commonly suffering from stocking in such places that are flat and usually are called plateau, like SGD. But for instance, other optimizers like ADA delta or RMS prop, they can escape these local these plateaus and basically reach a better minimum. So these optimizers, that they have their difference is the scheme that they update these parameters. Okay, so the choice of the optimizers and also the choice of the learning rate is extremely important in the training of our model. As you can see, if you choose a bad learning rate, or if you choose a bad optimizer, you might not be able to properly train your model. Here, if you choose a very large learning rate, if your my steps and the pace, and my pace is very I'm choosing a big step, you might jump to this side. Instead of going downward, you might jump to this side, and suddenly your loss would be greater, not smaller. And then you might jump to this part, and then again going back to the place that you were, and jumping up and down, and basically oscillating on the same parameters that you had before. So the choice for the learning rate and the choice for the optimizer are very important. And if you want to put things together, the training of a neural net is usually done by iterating over the training set for several epochs. We'll talk about why we need to go over the training set several times, but each loop in each epoch, again, comprises of going over the training samples one by one. For each sample that I have in my training set, so right now you are familiar with the notion of what is a training set, what is a validation set, and what is a test set. So the training set and the validation set are used for the training purposes, and for they're exposed to our learning algorithm during the training phase, but the test set usually kept undisclosed, and then when you want to actually evaluate your model, you are using the test set. But you are going over your training set one by one. You are giving your input sample to your network, which I'm abstracting here by f of x. It can be a multi-layer network with different nonlinearities and so on and so forth. It gives you a prediction. You are calculating the loss value and the gradient for the loss. You are passing this the gradient of the loss to the optimizer, and the optimizer is responsible for updating the parameters based on the gradient of the loss. Then you go toward the next sample, and you do this process for n epochs or multiple epochs until you have a desired loss. Yeah, the value of the loss is decreased. So let's implement and let's put things together. But before going to the implementation, let's see if I change the activation function from the linear. Remember, I had identity function as my activation function, which was linear. Now I want to change it, for instance, to relu. Okay. Now, if I try to separate the two classes, you can see that it can easily separate the two classes, right? It can approximate a more sophisticated function, or I can have a hyperbolic tangent here. It would take some time, but eventually it would converge. If you feel that it's not converging at your ideal pace, you can change the learning rate, or increase or decrease the learning rate, such that you prevent the oscillations that you might have on your loss. For instance, if I choose a large learning rate like 10, you can see that here I have weird oscillations, and you can see the value of the loss is not actually decreasing. Why? Because my parameters and the value of loss is oscillating up and down. It's not changing. However, if I reduce my learning rate to 1, it would be somewhat better, right? You see that it's oscillating. You see that the oscillation here that I have when I'm choosing a bad value for my learning rate. However, if I reduce my learning rate and start again, you see that I have less oscillations. You see I had less oscillation, but more oscillations in the beginning. If I reduce my learning rate again, I'm hopeful that I would have less oscillations. So you can see and appreciate the different strategies of choice for the learning rate and how it affects your problem. If you are using a very small learning rate, you can see that it might take a while for this problem to converge, and you want to get done with your problem and your training as soon as possible. So it's taking a lot of time. So the way that you are choosing your value for the learning rate determines the speed. So now let's talk about the implementation. For the implementation of this this simple network, I'm using PyTorch. PyTorch is developed by Facebook, which is a library, which is a deep learning library. It's a very convenient and easy to use library for the research purposes. Other deep learning libraries also include, for instance, JAX and TensorFlow and so on. But for our purpose, we are using PyTorch. So you can import. So let me connect to my notebook and let me share this with you. If you don't have it, let me share this in the chat. So yes. Yes, I shared this link with you. You can simultaneously look at this. So I've connected to this. I can import Torch with import Torch. This imports the whole PyTorch library, and then specifically I'm interested in neural layers. This torch.nn, import torch.nn as nn. It includes many standard neural layers that are useful for my implementation. So let me have a sip of my coffee. So first we are interested to let me clear the output of all of these cells. Select all cells. So first we want to have a single layer net. So if you can see, I'm implementing this single layer net as a class. Okay. Why? Because it's always good to develop your models with an object-oriented approach. Why? Because when you are done with the development of your model, then you can deploy your model. You can provide this model to other people, and other people can benefit from all of the benefits that an object-oriented program provides. So I'm defining this network as a class with the name of single layer net. I'm declaring this class as a PyTorch module. Later, I would mention the benefits of this PyTorch module and having it as a PyTorch module. So a single layer net only has one layer, the input layer. The input layer actually maps the input to an output. So it was linear. I can declare a linear layer like this, nn.linear. And the first argument here, when I'm declaring and making an object, is the number of the size of input, which is 64. This is totally arbitrary. These are the values that I chose. But you can change these values. It doesn't matter. Depending on your problem, depending on what is the number of input and what is the number of outputs and what are the number of classes, you should change these values. So I'm assuming that I have a 64 inputs and 10 outputs. Okay. So in this initialization, or some, this is something like a constructor for those of you that work with Java or C++. This is acts as a constructor that initializes the values. Then I have a forward function. Okay. So this forward function, if you declare for a PyTorch layer, if you make your layer a PyTorch layer and you have a forward function, whenever you are calling an object of this network, the network is automatically run through this forward function. Okay. So let's come back to this forward function in a minute, but right now I have a single layer net. I made an object called model out of this single layer net. Then I have a random input. This is a totally arbitrary input. Okay. So this is a totally arbitrary input. Then I'm giving this input to my model and expecting an output. As I mentioned, when I'm giving an input to this model, it automatically goes to this forward function if it is declared as a torch and a PyTorch module. Okay, so this input goes through this forward function. It is passed through that input layer that I had I had before. Okay, and then it calculates an output, and then this output is returned. Okay, so let's run this piece of let's run this. Okay, I have not imported this. Let's first import torch and torch.nn. Then let's run this. So this is my output. As you can see, so I printed the output. The output looks something like this. It has 10 entries. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Why? Because I chose this linear layer to map my input to an output. I see there's a hand. A hand is raised.
Yeah, I was gonna say, yeah, we got a few questions. Maybe we can answer them now before we move forward.
Yes, sure, absolutely.
Yeah.
So
I can read them. So, someone, Parisa asked you to zoom in a little bit.
Oh, okay, for this, huh? Okay, sure.
Yeah, okay, great. That's big. That's good. And then we have some previous questions which Sammy has answered. Thank you very much, Sammy. Edward had a question from your slide. What is the error margins? What is the line between error margins and the line and the loss function? Yes, and then we have some other questions about.
Okay, so that's a good question. That's a good question. That apparently it shows that he understood the support vector machines from the previous session. So here for our neural net, and here at least with this loss function that I chose, we don't define error margins like we do in support vector machines. Okay, because support vector machines, they explicitly model this error margin, but at least here we don't do error margins. Okay, so and I can explain later on this. Okay, but right now we don't have any error margins. So I can see that there are some questions on these 64 and 10 that I chose right now. These are again arbitrary values that I chose for my layer. Okay, depending on my problem, and I will explain how to choose these. Depending on my problem, these values might differ. So these are the values that I chose for the sake of demonstration. These are arbitrary values. Okay, so as you can see, again, my input, the input that I defined is a random input in 64 dimensions. Okay, it's totally random. The network expects this input to be in the 64 dimensions. Okay, if I provide an input into 63, then it would raise an error that you cannot do this because you have provided a 63 an input of size 63, and then you're expecting me to map it from 64. So these are totally arbitrary. And let me again talk about this my forward function. As I mentioned, if you define this layer as a PyTorch module, and if you define a forward function, you see when you're calling your model by this input and you're passing this input as an argument to your model, it automatically goes through this forward function. If I change the name for this forward function, for instance, I have it the forward underscore, we can see that this again would raise an error. It says module single layer is missing the required forward function. Okay, so since I have defined this as a PyTorch module, it requires a forward, and it does the forward pass for my network. Okay, then this is my output, and I can see the shape of my output. Okay, now let's add multiple layers. Let's add more layers. So adding more layers, as I mentioned before, is basically having more projections in our network. right? Here in the single layer net, I only had one layer. I only introduced and declared one linear projection here. In a multi-layer network, I have multiple projections, okay? An input layer, a hidden layer, and an output layer. Again, these projections are arbitrary in size, okay? I chose, this is what I chose as my hyperparameters, as the mentors are mentioned in the chat. These are hyperparameters, except the input and the output. The values that I have here are totally arbitrary and needs to be selected during the design of your model as hyperparameters, because the input, your input size is fixed. You are being provided by an image. You are being provided by a set of feature vector that it's not up to you what is their size. Their size is fixed usually, okay? And also the number of classes. The number of classes again is fixed. If you want to separate between 10 digits, it is again fixed. It's not up to you to choose what is the number of outputs. But the intermediate layers, it's up to you how many layers and how many neurons or how many outputs do you want in the intermediate layers. But these values again are hyperparameters that I chose. And so I have declared this 3 layers. Now I have changed this my model as a multi-layer network. In my forward function, I'm passing the input into the input layer. I'm getting H1. Remember, this corresponds to this to what I had in the slides. Then I'm passing H1 through the hidden layer. I'm getting H2. Then I'm passing H2 into an output layer and getting an output. Here, I also can print the size and the shape of these hidden representations. So I'm making a model and I'm making an object of my model from multi-layer net. Again, I have a random input of 64. My network expect an input of 64. Then I have an output. If I run this, you see that the hidden size for the H1 is 128 as I intended. Why? Because the input is mapped, 64 is being mapped to 128, right? 64, the input is being mapped to 128. So H1 is 128, then 128, again, I chose it. 128 is mapped to 32. 128 is mapped to 32, and I have this. Okay, and again, I can print here my output. Okay, this is my output, and I can again print its size, its shape, output.shape. You see the shape is 10. This is what I intended. Here I can change the shape to 100, okay? And the shape would be 100. You can see that I have a bigger output with more dimensions, and the size is 100. Okay? So now with the same steps that I had during the tutorial, I'm presenting these materials. So now let's add nonlinearity. If you remember, after applying each projection, we are adding nonlinearity. Okay, so instead of just passing H1 as the result of first projection to the next layer, okay, what I do is I first have that projection, then pass it to a ReLU function, and then this H1, which the ReLU function is applied over, is being passed to the next layer. The next layer, it has a hyperbolic tangent, and so on and so forth, right? So it's simple as that. Just torch.relu or other activation functions that are defined in PyTorch, or the activation functions that you can define, which is a little bit away from our discussion. But there are a set of activation functions here. I can change this for sigmoid. Okay, and it suggests here. Now this network, this 3-layer network, now has the capacity to approximate more sophisticated functions. Okay, So just one thing before going to the next part, you can see this is my output. This is my output that has 3 dimensions. As you can see, I have negative. I have also negative values here. However, before returning, I can pass this output into a ReLU activation, for instance. So torch.relu. I'm passing my output before returning. I'm passing it into ReLU. Now you can see that all of the negative values here are turned to 0, because from minus infinity to 0 for my ReLU activation, I had 0, and the rest remains the same. So here I have 0, 0, 0. It has filtered out the negative values. Okay. So, but let's keep this network as is. It was hyperbolic tangent, or I can have ReLU here. It doesn't matter. So this is my network. This is a network, a multi-layer network with nonlinearity that I can use to train, to do training on a data set. So for my purpose, I'm using the MNIST data set, or the digits data set. It is available from sklearn data sets. Okay, this is a data set that can be sklearn provides a set of data sets for the beginners to work with and to experiment. So I'm loading this the MNIST or digit data set. This problem is a classification problem. This data set is labeled for 10 digits, starting from 0 until 9. So 0, 1, 2 to 9. We have 10 digits, and the problem is to classify an image of a digit for the corresponding digit, whether it's a 1 or 2 or what. Okay, so at the beginning, I'm using the train test split utility provided by scikit-learn. I suggest to you to get familiar with these utilities that scikit-learn provides for you. Train test split. Because I want to split the whole data into a test portion and a train portion, into a training set and a holdout set. Okay. So I'm choosing 20%, and I'm holding out 20% as my test. Okay. And the rest for the training. Okay, so I have my training data, and I have my test data, and I have my training labels. Okay, so let's just have a quick look at this data set. Let me zoom out a little bit. So here I demonstrated I've illustrated 2 samples here. One is 0 and one is a 5 digit so digit 0 and digit 5. So hopefully, if you provide this digit to our train network, it needs to predict 0, and if we provide this, it needs to predict 5. Okay, so here once we have defined our network, we then define the loss function that we are using to optimize this network. And we use an optimizer out of the set of available optimizers that are available from PyTorch. For this tutorial, I'm using Atom Optimizer because it's a relatively good optimizer that is robust optimizer that prevents falling into plateaus and sticking into plateaus and so on. So I'm giving the parameters of my model that I defined before. Here you see I have a model here. I have a multi-layer net model. It has a set of parameters, right? What are the set of parameters for this model? These layers, right? These projections that are trained. Okay. So, and I'm saying your learning rate is this. You can experiment with this learning rate, and we would experiment with this learning rate and see what is the effect of this learning rate. So, but before going over the training, I should mention that a feed-forward, the input to a feed-forward network is always a vector. However, an image is a matrix. Okay, so how I can use a matrix as an input to a feed-forward net, a common solution, which is a very old-fashioned solution, is to convert this matrix into a vector and vectorize the matrix. How? So we are concatenating all of these rows, row 0, row 1, row 2, and attaching all of this to the first row. So we are moving the first row and attaching it at the end of end of row 0. The second at the end of the result that we had. So here, since I have 8 rows and 8 columns, I have 64 elements in the resulting vectorized input. Okay, and that explains why I chose 64 here as my input size, right? And how many classes do we have? We have 10 digits. We want to classify it into 10 digits, and that explains why I chose 10 as my output. Okay, so I've loaded the training data. Now let's loop over the training samples. As I mentioned before, we are going over the samples for several epochs. Here I have 10 epoch. Okay, so I'm going over the samples one by one. First, I'm setting the gradient of the model, that what is stored in my model, the gradients that are stored in my model, to 0, because I want to have a fresh set of gradients for the current samples that I'm passing through the network. When I'm passing a sample through the network, the model automatically calculates the gradients based on the loss that we will have later. And when we are going over the next sample, we should forget about the gradients that were stored for the previous samples, because there is a new sample at hand. Okay, so we are making sure at the beginning, we are making sure that our gradients are set to 0. We are passing the first training sample to the model. Then we have a prediction. Then I have a loss function which measures the closeness between the prediction and the training label. For this sample, I have a loss. Then I call the backward function. This backward function calculates the gradient based on the current sample. Then I apply these gradients through this optimizer using this step. I'm saying go one step, do one iteration for your parameters, update the parameters with respect to this loss that I have. And then I'm storing the value, all of the values for this loss for this current epoch, to show what is the average value of the loss for my current epoch. So then I'm going over the next sample, putting the gradients that I calculated here before to 0, going over it several times. So this would look, yes, I have not executed this. Let me execute this. So this is what the training would look like for this network. First, the average loss is 1.6. Then you see that the value of the loss is decreasing, right? 0.5, 0.2, 0.2, 0.16, 0.13, 0.11, 0.10, 0.08, 0.07, and you can go further, okay? And I would tell you when to stop and when to go further. So do discuss about this. But for now, I feel that this the value of the loss that I have has been minimized. It's good. Okay. Now it's time to do and really evaluate our model to see how much our model is performing on the test set. So I'm doing the same way that I had. In the same way that I had, I looped over the samples in the training phase. I would go over the test data. Okay, so I'm going over the test data. I'm passing the test sample into my model. I'm getting the prediction. Then the prediction, I want to, if you remember, I said, look at the neuron or look at the output that has the greatest value, has the largest value. Which neuron has the largest value? I'm getting an argmax of my prediction. So this prediction here is is a 10 dimension long vector. You can see that here it is showing, it is telling me what the Colab already gives me what is the size. The tensor or the size of my output is of 10, the same number as I have for my classes. Then I'm getting an argmax. This prediction would be either 0, 1, 2, 2, 9. Okay. Then I'm gathering all of my predictions in a list. I'm getting all of my gold labels in a list. Then once the loop over the test data is finished, I'm evaluating my model using sort of metrics that are provided with sklearn like classification report. So let's loop over my test data. This is on my test data. You can see very detailed information on different classes. For class 0 until class 9. What is the precision, what is the recall, and what is the F1 score? So if you remember from Dr. Aziz's talk, F1 score is basically a harmonic mean of recall and precision, because a high precision is not enough, a high recall is not enough only in isolation, but a good system ought to have a high precision and high recall simultaneously. You don't need a system with very large high precision and very bad recall, because one can obtain a very large precision by having all of the samples and declaring and predicting all of the samples as negative. Okay, and then you would be very precise. Your precision would be 100, and you can have a perfect recall when you have all of the samples and declare all of the samples as positive. But that's not really good. So you need to have a balance and harmony between the precision and recall, which is realized in the F1 score, which is the harmonic mean of the two. So this support means how many samples of this class I had in my test set. So 41 samples from 0 and 40, for instance, from 80 and so on. So overall, you can see that our model did a very good job, because I have a high F1 score for most of these classes. So one thing that I can do is to basically change the number of. So let me have a fresh model. Okay, now I have a fresh model. Let's change the number of epochs for instance, to 3 epochs. Okay, and see how this affects the performance of my model. Okay, I only did it for 4 epochs, and then let's make a set of new predictions. You see, for 0, because 0 is a very easy class, it has a better, it's still good. But I have 86 here. I had 89 here. If I do it for only 2 epochs, the performance would be even lower. Okay, so there is a balance. There is a balance between the number of epochs and the performance that one gets for as a result. So let's have for instance, let's have it for only 1 epoch, and then let's evaluate our model. You see, it decreased dramatically. For instance, for digits 8 and for classes 8 and 9, I have a bad F1 score, but still. For instance, here we can see for 0 or for 6, because they are very easy classes. They have model has learned to distinguish between the 2 classes. So that basically concludes my talk. I'm open for questions if you have any. Remember, I have shared this link with you. You can use it and then explore different possibilities, play with the learning rate, see how it affects. And as a bonus, I also have provided a code for autoencoders. We can later talk about autoencoders, but before finishing my talk, I want to talk very briefly about convolutional neural nets, because you also have convolutional neural nets in your later steps in this course. So right now, you just saw that when I wanted to provide an image to a network, I had to turn that image to a vector and vectorize that image to pass it through a feed-forward net. However, convolutional neural networks, they can and are able to get matrices as their input, rather than operating on vectors. Are also able to operate on matrices. Okay, because an image is a matrix. So a convolutional neural net also is characterized by a set of weights, by weight matrices. But these weight matrices, if I zoom in, the small matrix that the smaller matrix that you can see here, that it has a smaller values, 0, 1, 2. These are the values of the parameters that I have here. This matrix is it's a sliding matrix. So we slide this weight matrix over our input, over an input image, and we are multiplying the corresponding values together. So 0 times 0 plus 0 times 1 plus 1 times 2, and so on and so forth. And the result would be added and aggregated into another matrix and another entry. Okay, so this sliding function allows to have an abstraction and have another representation of this matrix. Then we can use this. We can apply another filter over this. Okay, and then further abstract our input and have it into a vector later, and then use it to classify our image. So usually the convolutional neural nets, the exploration and inspection of convolutional neural nets reveals that these sliding matrices, which are also called filters, they allow and are able to capture specific features in the image, like edge features, textural features, and so on and so forth. This illustration is taken from Piano documentation, which was a very popular library developed by University of Montreal. So that's basically concludes my talk. Eugene, you go ahead if you wanted to take it from here.
Yeah, thank you so much. I think we can start asking questions now. If
okay, sure.
Yeah. Do we have more questions from the? Yeah, I see that there are questions from the participants that were answered by our mentors, but maybe we can go back to them and explain a little bit further. Okay. Let's see. Let's scroll up. Yeah, we previously got a question when you were explaining the slides about how to choose the so-called correct learning rate and optimize.
So the learning rate I mentioned here on the TensorFlow Playground. You can see that you always when the most important weapon or the measure or statistic that you have for training your neural net and for your neural net diagnosis, as I say, is the value of the loss. If you see that the value of the loss is oscillating, it's jumping up and down, you need to, most of the time, not all of the time, most of the time, reduce your learning rate. Okay, so to move on the surface with a smoother pace and with a smaller pace. So that helps to looking at the loss function allows you to determine a good learning rate. So that's for the learning rates by looking at the loss function. Also, by looking at the loss function, you can see that how many epochs you need to go. Okay. So yes, let me just, but before I forget, let me share the link to this TensorFlow Playground. Yes. So here is the link to the TensorFlow Playground. So how many epochs when you look at your loss, across from different epochs, when you see that your loss is not moving after a certain number of epochs, okay, you can stop and say, okay, if you first start, for instance, for epochs, and you see no, the loss is still decreasing, then you can continue your process. But apart from the value of the loss that you have, you can also have a third set, as we call it, a validation set. After the end of each epoch, you validate your model on a validation set. Just like I validated my model on a holdout test set, I validate my model and I evaluate my model on a validation set. Then I have a performance like accuracy or F1 score or precision or recall, depending on what is most important for you. Then you evaluate your model on that. And across epoch, you check and you trace and you observe this value, whether it's going down, the performance on the validation set is going down, and it's going up. Okay.
Yeah, and I think in future workshops we'll also see the plotting of loss functions as you're training over the epochs, and we'll explain more on cross-validation as well. Okay, and then we can go to the next question. Greg was asking, how does the 64 by 10 dimensions relate to the model equations you showed earlier? I think you explained the dimensionality choices many times now, but we can go over that again, I guess. But
yes, so as I mentioned here in my training, so as I mentioned, the input and the output is defined. The number of inputs and the number of output is defined by the problem that is at hand, by the data set. What was the number of inputs that I had, the input size that I had for this problem? So originally, the input is a matrix, but since the feed-forward nets, they basically cannot take matrices as input. First, I turned this matrix into a vector, and then provided that vector as the input to my model. So the size of that vector was 64. Why? Because overall I have 64 entries in this 8x8 matrix. Okay. Mm-hmm. So that's for the input. So I had to declare 64 as the size was my input. However, the output was 10 because I had 10 classes. So yes.
Great. Can you share? Yeah, everything has been uploaded to Gumroad if you want to go see. Can you comment on this question? Oh yeah, so that's been answered. Cross-validation. We had a question on cross-validation as well. Sort of just explaining what is it, how to use it, different types, k-fold, stratified k-fold, whatnot.
So the objective of this tutorial was to first, it was the first tutorial to expose you with PyTorch and the basics of the PyTorch. Okay, but apart from the deep learning or machine learning model that you're using, it doesn't matter you are using a neural net or a transformer or what. It is so cross validation or an evaluation of your models is agnostic of the method that you're using. Okay, so apart from this. There are certain approaches for evaluating a model. Okay, apart from more traditional train and test sets. Okay, so for instance, we have an approach called k-fold cross validation. So this k-fold cross validation, why we need
maybe you can Google a figure of that so that
yes. That's a great idea. K-fold cross validation. Yes, k-fold cross validation. So k-fold cross validation. Yes, this is a no. The other one is better. So k-fold cross validation. What is the need to what is k-fold cross validation and why we need it? So one might argue, and one of you might argue that that this test set that I chose, it was by chance, and my chance was good, and this was an easy test set. You had all of the samples that were easy, okay, and your model was not really good, but the test set was very easy. So to address this concern, we use this splitting that we had several times, or for k-folds. Okay, so the type of splitting that I had for here in my code was mostly something like this. That for instance, I randomly picked one of the a subset of the data as a validation or a test, and the rest I use it for the training. And if k-fold cross validation, we are partitioning our data into k-folds. Here I have 5-fold cross validation. Okay, so I'm dividing and I'm partitioning the data into 5 folds: 1, 2, 3, 4, 5, and I'm iterating and I'm going over these different folds. So for the first fold, I'm using it for the test, and the rest for the training. Then I have a measure. I have a F1 score, for instance. Okay, and then I have a second fold here. I'm using it for the test and the rest for the training. So overall, I have 5 folds and 5 performances on different sets and different partitions as a test set. So I can average these 5 performances like this. I can also report other measures like variation or standard deviation of different of the performances on different folds. So a model that provides, for instance, a low variance or low standard deviation between these performances is preferred over a model that has large standard deviation. Okay, because we want our model to be predictable and robust in actual deployment. Okay, and we want our model to be the behavior of our model to be a little bit more predictable. So yes, that's basically cross validation.
Thank you very much.
But the point is these validation strategies are agnostic to the type of model that you are using. It can be a decision tree, it can be an SVM, or it can be a deep neural net. It doesn't matter. All of these evaluation strategies can be applied to these models.
Fantastic. And then we have another question from Hanie that about how to determine how many epochs is good enough for a model.
So yes, I mentioned if you have a validation set, and if you are looking at the performance on the validation set, and also the value of the loss after your performance is not getting better, okay, or the value of the loss is not decreased after certain epochs, you then stop. Why? Because if you continue, you might have a problem of overfitting. Okay, and this overfitting is basically
leads to the next question pretty well. Someone asked about the concept of overfitting with respect to loss function.
Okay, so yes, with respect to the please sorry, there was a question that really intrigued me. It was about NLP. What is how to improve the transformer model using encoder method. So that's further down the line. So right now we are talking about feed-forward nets. With my talk on, I guess it's July 18. I guess I don't remember.
Yes,
it was July.
It's starting the second phase.
Yes, I would be happy to discuss transformers back then, because that's basically my expertise is those materials. But so regarding to the value, yes, in theory there is always this possibility that we reduce the value of the loss to 0. Okay, but as the value of the loss gets smaller and smaller and is decreased, so the model is trying to fit to the training data very tightly. okay? And as we call it, it tries to overfit to the data, okay? So when a model overfits to the data, sometimes it cannot generalize well to the unseen samples and the samples that are not available. I have not and they have not seen in the test phase. So let me show you just for fitting. Let me regression. Let me show it into a regression problem, and then we can. So, for instance, yes, here it's a very interesting figure for overfitting. You see, this data that we have, this dots, these samples that we have, more or less is describing a linear function, okay, more or less, okay. But if you try to have a zero error or have a zero loss, okay, we might end up with a function that is fitted on the data like this. You see that for the training samples we have zero error, okay. But if I have a sample here, if I have a sample between maybe -5 and -4 here, the value, sorry, the value that I have, the value is a very some sort of an outlier value. It's very far away from the actual value that is expected for this. Okay, this is because we try to hyper focus on reducing the error. Okay, so if we and we have actually increased the learning capacity of the model too much. Okay, so overfitting has many aspects. It depends on the learning capacity of your model. Are you trying to fit a nonlinear function on a data that has a linear distribution? You would commit overfitting there. Are you trying to hyper focus on reducing the error? You are committing overfitting there. Okay. But throughout the lectures, during our series, we will talk in detail about overfitting and the signs that are observed and the evidence of overfitting.
Great, thank you so much. And Greg asked another question about describing the encode and decode methods in the autoencoder. I think that slide of yours intrigued him. So if you want to go back.
Okay. So encoder, so autoencoder here, more or less, it has nothing to do with the encoder and decoder part in the transformers. Okay, because
he's not asking transformer. He's just asking to explain the architecture of an autoencoder, basically.
Yeah, I had this slide before. So yeah. let me Eugene go back to the AI I have this slide from the AI Research School. Hold on a second. Yeah. I can bring it very quickly. So, archive projects. Yes. Meanwhile, if any of you have any other questions, I can.
Well, someone also asked about the. Saurabh asked about the difference between loss function, cost function, and error function.
So yes, that's a really good question. That's a really good question. When we are talking about cost function, we usually we are reminded on more general optimization problems. Okay, note that also the training a neural net is some sort of an optimization problem. Okay, but overall, these are related concepts. These are related notions, but each community and different fields, they refer to more or less same concept with a different name. So, for instance, in genetic algorithms, you refer to it as a cost function because you are trying to reduce the cost of an optimization problem, the cost of an activity, right? Because more or less the optimization problems are for instance, you want to reduce you want to reduce your travel expenditure, okay? You want to reduce the cost. Usually in the classical optimization problem and programming problems like linear programming or nonlinear programming, you're trying to reduce a cost. Okay, that's where the term cost comes, and you are not necessarily having any error there. Okay, you in an optimization problem that you want to travel between a set of cities, and you want to choose the best way, the best road to go with the least distance. You don't have any errors there. It's more of a choice of the cost of the fuel that you're putting there and the cost of your time. Okay, so these are related concepts, but the point is some of these concepts are not applicable to other settings. So you don't. So here, as a matter of fact, we also have a cost. So the loss can be expressed as an error, can also be referred as an error, and also can be expressed as a cost. But it's not the same vice versa. For optimization problems, sometimes we don't have any error, or sometimes we don't have any loss. We only have cost. Okay.
Great. Thanks so much. Yes.
So let me briefly talk about autoencoders. So autoencoders are feed-forward networks that are trained in an unsupervised fashion, and despite what we talked about here about supervised models. So far, we have talked about supervised models. Dr. Azizi talked about supervised machine learning. I've talked about supervised machine learning because I had labels. But autoencoders and unsupervised models, they are not using any label provided by any experts. An autoencoder has two parts: an encoder and a decoder. And usually, not all the time, usually they are the mirror of each other. Okay, so we are providing an input to this encoder. Usually we have a reduction in dimensions. Then we have a representation in the middle. We try to reconstruct this representation at the input representation at the output representation. Okay, so here, since these values are randomly initialized at the beginning, when we are giving an input, the output is somewhat garbage. Okay, the output is very far away from the input that we had. But we are trying to change these parameters such that this input is reconstructed as this output. And one might say, okay, what is the benefit here? The benefit is that then once the training is finished, we are getting rid of this decoder, and we are only using these representations provided in the middle. Okay, so what is the justification here? These representations that are provided in the middle and obtained in the middle, they were so good that one could reconstruct the initial input from the output. So one can argue that this, instead of having a representation in higher dimension, only use the representation in lower dimension. Okay. So yes, that's so yes. We usually this middle part, this intermediate part, is called the bottleneck. The bottleneck for this autoencoder, and it has different. This representation in the bottleneck is referred by different names. Some refer to as latent representation. Some refer to as reduced representation. But the point is, it's not always the case that it's a lower dimension. It might be in a higher dimension, but it makes sense to have it in lower dimension. So yes,
wonderful.
That's
awesome. I think that was the end of all the questions. Yeah, thank you so much, Parsa. I think that was very engaging, and everyone understood a lot from both the slides as well as the detailed explanations of the code. So
I was happy to contribute.
thank you. And you will see Parsa again for 2 more sessions for the transformers. And what's the other session you're going to give?
So first, we are going to talk about natural language processing.
Yeah.
An introduction to natural language processing, and then transformers.
Fantastic. Yeah. So see him again. Thank you so much, everyone, for joining today. And we'll keep in touch. And don't forget about the tutorial session on Thursday at 1:30 p.m. Eastern Daylight Time. See you next week. All right. Bye.
Bye.